Welcome everybody to Probability and Analysis webinar. Today it's our great pleasure to have Arnaud Marsiglietti from University of Florida, who is going to talk about moments, concentration, and entropy of log-concave distributions. Please, Arnaud, feel free to start.
Thank you, Pata, for the introduction and for the invitation. It's a great pleasure to be here and give a talk in your seminar. So today I will talk about log-concave distribution in the discrete setting. There's a lot of work that has been done in the continuous setting, and a lot of questions arise more in discrete math about, okay, how can you understand in the same way, like the geometry, distribution, and so on, about the log-concave distribution in that discrete setting. This will be joined with James Melbourne, and maybe just to remind everyone about log-concave distribution. It's very simple, like notion, easy to understand, and that was very old notion. It was introduced a long time ago. If you are looking at, let's say, a sequence is log-concave if an square is bigger than an minus 1, an plus 1. That's so a simple property to understand, and it turns out that this appears in a lot of area. If I just ask you, what's your famous discrete distribution? Most likely you are going to cite, let's say, Bernoulli, binomial, geometry, Poisson, and they're all log-concave. And there are many more distributions that satisfy this property. And so it's appear very naturally. In probability statistics, there is this notion of positive dependence. And it turns out that log-concavity is a good notion to understand negative dependence. Of course, if combinatorics, they all know about log-concavity, and there are like very famous conjecture that has been recently solved about matroid. And if you followed lately, who got the field medals recently, Jun Hu, he got his medals based on his work on log-concavity in the discrete setting. So this has been around a long time ago, and it still has a lot of interest. So this very important notion in many aspects. So for example, there is also those property in information theory about maximizing distribution. This is a very important topic in that area. And it turns out that log-concave distribution are among maximizer. So they appear naturally in those contexts as well. There is a old result that attributed to Newton. If you have a sequence of a positive number, and if you look at a certain polynomial, if it's real rooted, then the sequence is log-concave. So it's a way to kind of have a criteria to determine whether sequence is log-concave or not by looking at polynomials. So also some connection with algebra here. And of course, in convex geometry, there's this very fundamental notion of mixed volume. And if you look at this notion of mixed volume, then they turned out to form a log-concave sequence. So you see a lot of different areas, and this appears more or less everywhere. And so it's a very important notion. In the continuous settings, things that we are more familiar with, if you look at the log-concave density, log-concave function, it's log-concave. So if, again, log f is concave. And the same way it appears in many cases, if you are looking at continuous distribution, it's going to be like, if you think of Gaussian exponential uniform, they're all log-concave, basically. So this is also something that appears naturally in the continuous setting. It has nice property in both cases, discrete or continuous. If you sum independent log-concave random variable, it remains log-concave. So that's nice stability results for this class. And in fact, you can easily make, so there's some equivalence between the two in the sense that given a log-concave sequence, you can build a log-concave function out of it. That's very simple. And if you just restrict your log-concave function to the integer, it's going to be a log-concave sequence. Now the normalization will be different. If you want to look at densities, it might not be a density anymore, but up to some constants, you can try to get some results. There is another notion, maybe less known, which also actually allow you to have a more comprehensive theory, more general results. Log-concavity can be a particular case of like relative log concavity. In some sense, if you just divide by some mass function, actually it doesn't have to be a probability for Z. I just put it this way for simplicity, but just a non-negative mass function with convex support. If you divide and you get something log concave, then you can say it's log concave with respect to Z. This will be very important later in the result because we get some more general results. So imagine, for example, if you take simple case of constant, because if you want to get the regular log concave, you can either take constant 1 all the time. That's why I'm saying that you can extend it to not necessarily distribution. It could be just a positive measure. But if you look at geometric, actually, it's going to give you log concave as well. So you can get both ways. Some important examples here. If you look at binomial, you get what is known as ultra log concave of order n. And those are so subclasses of log concave distribution, but they are stronger. And so you should expect better results. So if you remember, we are interested in, let's say, distribution, concentration, moments bound. We'll get stronger result if we can understand if your variable is log concave with respect to some specific distribution. So if you have a binomial, then you get stronger form. And for example, it's the case for the mixed volume of a convex body. They are stronger than just log concave. They're actually ultra log concave. And so n will be the dimension in that case. So you can get some stronger result. And this will give you better result, and we'll see that later. So the binomial gives you ultra log concave. If you look at Poisson, it's in some sense a limit of binomial, so you get slightly weaker statements, ultra log concave, but it's still stronger than classical log concave distribution. So you should expect better result as well for that subclass. And so the constant in front, 1 plus 1 over k, bigger than 1, so that tells you it's slightly stronger. And regular log concavity is by taking geometric, and you get just a standard notion of log concavity in this case. All right. So in the same way, you can discuss relative log concavity in a continuous setting, and there are some famous case where you want to consider, for example, G to be a Gaussian, and this gives you ultra log concave, or like strongly log concave is usually how it's called. The class of strongly log concave on a variable, you have this factor in front, exponential t1 minus t, and the distance between x and y. So if you look at the same type of definitions, then you can get stronger type of log concavity as well. So our result will hold for both continuous and discrete. We are going to focus more on the discrete case, but what I'm going to mention later works in either way. It's actually going to be more general. In some sense, you can think of log concave with respect to some measure, and you can derive result for that subclass. The standard log concavity is just exponential, or just a constant 1 for G, and you go back to log concavity. So you can get different classes, subclasses, and you should expect stronger result depending on what you are putting as a reference measure in some sense. So now I'll describe the main results that we have, and they all follow from the same technique. First one is a tail bounds. We want to describe large deviation, small deviation from the expectation of a random variable. So in this case, you have independent discrete log concave random variable. You look at the sum, so very standard result. And what you can expect is exponential concentration, and you can kind of have explicit values on the constant. It's based on the first moment, and you get some sort of t minus log t. Here you recognize the bound of the exponential distribution. And there is a reason for that. Actually, for just exponential distribution, there is a paper recently, for some reason, that so there is some motivation for geometric random variable. There is a result of Janssen 2018, where basically you get this bound for exponential distribution. And so this was motivated by some question in computer science. So it has their interest, and but geometric being just a particular case, you can imagine the big picture is log-concave with respect to geometric. You should expect that log-concave has the same property as geometric if you can try to pass from this whole class. So basically, you can describe this whole class of log-concave distribution with just one, which in some sense, in this case, a reference measure. And that's the main idea here. So what we get is that no matter what is your log-concave distribution, is going to be to have the same result as geometric. So what you get for geometric holds for any log-concave. Now, if you remember, there is what I mentioned, that you can have a reference measure. It doesn't have to be discrete or continuous. Both will work. Actually, you can have more general results. And the same, in the same paper of Janssen, he deals with both discrete, so the geometric distribution and the exponential distribution, and get those tail bounds. What we have is, of course, more general, where it applies to all log-concave, either discrete or continuous, because it's not actually not really important. There's I guess, more general feature here. And so basically, you can get the same result for exponential. You get it for all log-concave distribution. So here I just put a normalization, expectation equal 1. It's not very important. You can put that into your constant lambda I. But basically, you get, so the general result is you get the same type of bound. So it's very similar. So again, you can expect exponential concentration or exponential bound for this log-concave distribution. So I'm not going to write down the formula, but in fact, we have more general results. It's not just for this subclass of log-concave. So again, if you restrict to, let's say, those binomial distributions, so this ultra log-concave order M, you get actually the same bound that you get for Bernoulli. So Bernoulli, you should expect better concentration, better tail bound. And so for this subclass of log-concave order M, you actually get the same bound. So again, if you can determine if your random variable is log-concave with some reference measure that satisfies some tail bound property, then it's going to hold for the whole class and not just for one distribution. If you look at the basic textbook in large deviation or concentration inequalities, all the results are known for specific distribution, so Bernoulli, Poisson, exponential, but that's pretty much it. Or you have compact support, but then it will depend on your support. You don't have bounds that are kind of independent of your support or dependent of the number of summand. And in the class of log-concave distribution, you actually can expect that. And that's much more general than just those specific distributions that you have. So concentration for Bernoulli hold for all log-concave order M. And I will specify that for Poisson because we actually got using different techniques. So this was with a student, one of my students, Eshan Aravinda, and also with James Merbourne. In the case of ultra log-concave random variable, you can get it either way, either saying that it's with respect to Poisson, and or taking limit when n goes to infinity, if you are looking at Bernoulli. And here you see that this is a well-known bound, but for Poisson distribution. And it turns out that this well-known bound is actually true not just for Poisson, but for all ultra log-concave random variable. And this is very important. That's back then when we got this result, so there is a paper that we were interested in because they are proving some kind of concentration result for a specific class of distribution, which was based on the mixed volume. So if you remember what I said earlier, mixed volume are log-concave, but it's actually stronger than log-concave. They are ultra log-concave. And so there is this paper of Lotz, McCoy, Nordam, Pecati, and Trop. And what they prove is that for intrinsic volume random variable, So there are some interest in like statistical learning. They have lots of application to understand concentration of those interesting volumes. So they have an explanation is like for those threshold phenomena in sort of statistical learning. And then they arrive to some concentration bound for those interesting volume. But interesting volume are ultra-log concave, and so if you derive a bound for all ultra-log concave, then as a result, you get it for those specific distribution. And so you need to see log concave as not just log concave, because you won't get very good concentration, but if you know that they're actually ultra-log concave, then you can actually get those Poisson concentration bound. And those bounds that you see here actually improve what they got. So their argument was very specific. They actually go from the continuous setting. There are known results, like concentration in the continuous setting, and they go back to the discrete. So of course, when you go from continuous to discrete, you lose the constants. The constants are suboptimal, and you kind of don't get, so you get weaker bounds. And what we have is, of course, optimal, because you could realize some mixed volume as Poisson in the limit when it's asymptotically optimal as the dimension goes to infinity, and you cannot really get better bound. So not only we have the result for all ultra-log concave, but in particular for those interesting volume, but all of them. And so, and the proof is actually simpler in that case, but it turns out that what I will show today, there is an even simpler proof. But here we use some sort of, so in the continuous setting, there is this localization techniques, which is well known, which basically, if you have seen the geometric form of Fradesi and Guédon, it's basically it's an extreme point problem. So you can reduce that technique to identifying the extreme point, and by like a Crane-Mimard argument, you know that you want to maximize a convex function, you just need to look at the extreme point. And that's what we're doing in a discrete case. We actually develop a discrete version of that statement. For discrete log concave, you can find extreme points, and then you can try to then calculate on the extreme point and get the result. And that's pretty much what we did in that case. So identification of extreme point, and you calculate for those extreme points, which will be basically Poisson, but not just Poisson, truncated Poisson. So you calculate, you have a few, you run the algebra and you get the result. What we'll see at the end of this talk is that there's a much simpler argument, actually. Okay, so that was about tail bound and concentration bound. You know, there's some connection. So moment bound, the same, you can get actually a very general result. If you look at log concave with respect to some random variable z, if you fix the moment of order alpha, then you get a moment comparison, which is well known in the continuous case. So those are like Herder type inequality. It's known that if alpha is less than beta, then the moment goes increasingly. But you can reverse the moment bound up to some constant, and that constant will depend on basically just one distribution, which is the relative log concavity that you are looking for. So in this case, if could be z, could be anything. Let me see if I have something else. Oh. Yeah. So in the continuous setting, this actually is good because you have a bound that's just dependent on alpha and beta. So this is very well-known result, Caroline Proch-Barlow. It's very well known in the continuous setting for just so regular log concavity in the continuous setting. So in this case, you take z to be exponential, you can calculate those things, and this turns out to be just a gamma involving gamma functional. So you just get explicit bound for A alpha beta. Now in the discrete setting, it's more it's actually more subtle because and more generally for other distribution, you might not have, so this might not just depend on alpha and beta. Actually, if you compute these things for geometric, there is a surprising thing that happens, is that it's going to depend on the distribution of, so in some sense, it's going to be more than just alpha and beta. It's going to be dependent on the distribution, on the parameter of z. And you won't get such a nice formula as here in the discrete setting. You'll get, it's going to involve a bit more things. For example, in the continuous setting, this tells you that the second moment is comparable to the first moment up to a constant. it's not true in the discrete setting. The second moment is not upper bounded by an absolute constant times the first moment. This is no longer true. So there is it's a little bit more tricky in the discrete setting. But this is still a general result. Let's say as long as this has a nice form, then you can get a universal bound between the moments. So there is a general idea for all those results that we'll mention a little bit later, but just to review a little bit what is known and to extend that to more general distribution. So you might be familiar. So this actually is a known result in the continuous setting. It's a result of Carlson in the discrete case where you look at factorial moments and you have some log concavity of the factorial moments. So yeah, I didn't write it down, but in the continuous setting, if you look at 1 over gamma p plus 1 integrating your density of a log concave function, so if you have a log concave function, we know that this is log concave. In the discrete case, there is an analog result. This was done by Carlson, but for just regular log concavity. And our techniques allow us to have more general type of statement where instead of just log concavity, you can have ultra log concavity or of order n and so on. And if you let n goes to infinity, you get like basically Poisson type bound. So in the discrete case that we read as, if you look at the factorial moment, basically you get a log concave sequence, which is similar to the continuous setting. And but this has been done in the log concave case. You can actually apply it to more general type of log concavity. You don't have to be specific to log concave. It could be with respect to some other reference measure. So yeah, in the ultra log concave case is nice. It's just 1, so you just get exact log concavity in some sense. Last result, I will move on to entropy bound. I will just remind you a couple of entropic formulas. So you have Shannon and Rayleigh entropy more generally. So those can connect geometry, probability, and information theory by looking at specific parameter for the Rayleigh entropy. If you take alpha equals 0, you get log of the, so here I draw this as discrete, but if it was continuous, it will be log of the volume. In the discrete case, it will be cardinality. So you can connect to combinatorics. So there's non-result where you can have some additive bound using some entropic inequalities. You can get geometric inequality in the continuous case. Brun-Minkowski inequality is connected to entropy power inequality, if you have seen that. So you can easily connect combinatorics, convex geometry by looking at exponent 0 of your Rayleigh entropy. And infinity, it's connected to the maximum of the density or maximum of probability mass function. So it's sometimes called the concentration function, which also has application in probability, and that we're also considered. So trying to understand, for example, in the continuous setting, trying to understand the maximum of the density, you probably know that is connected to this slicing problem. So the famous Borgen's hyperplane conjecture is trying to estimate the maximum of the density of a log-concave function. So you can have some entropic formulation, some different characterization, and so on, using those kind of entropy function. Yeah, okay, so here is a continuous case. So same type of formulas. So there's a result of you who actually improved some previous result of that were like a few years back. In the case of ultra log concave random variable, the entropy is maximized by Poisson. So maximizing entropy is like very well-known topic. Has a lot of result in that direction. And depending on the constraint that you are putting, your maximizer could be different. So there is a famous result that if you just fix the first moment and you just look at log concave, then it's going to be geometric. And actually, this is always true no matter the shape constraint. It doesn't have to be log concave. So if the support is 0 infinity, you know that the geometric is going to maximize your distribution. So this result in the log-concave case is not very interesting because more generally it's known for any distribution. But now if you put some constraint, if you're ultra log-concave, so within that class, it becomes Poisson as an optimizer. And we can get some more general result where not only for Shannon entropy, but we can allow some Renyi entropy case. So if you have log concavity with respect to Z, it's not necessarily just Poisson, it could be like Bernoulli. And in this case, continuous or discrete, both cases work. So again, this is going to be maximizing the entropy. If you have discrete random variable X, which is log concave, if you fix, of course, you have to fix a constraint, so you are fixing the first moment, then that distribution that you are referring to is going to be the maximum. So you see there's some similarities between all those statements is that we can compare to one random variable, which is basically the reference measure that you are having in that class. Yeah, so if you are wondering what happened for alpha bigger than 1, it's no longer true. So we have explicit counterexample where for some reason, if you're log concave with respect to that to certain reference measure, that measure is not going to be extreme any longer. So this is tricky to understand the alpha greater than 1 case. But okay. So what is the main ID is actually known ID in probabilities majorization. And so it's run as follows. If X is majorized by Z in the convex order, if and only if, by definition, then the expectation of phi X is less than the expectation of phi Z. So the question is basically, can you prove that it's majorized? Because if you know it's majorized, then you'll get that inequality for any convex function. And convex function is, you can get a lot of, so all the results I mentioned before can be put into a convex function. And so the idea is actually also simple idea. If you look at a concave function, which is actually a known technique, you look at a convex function or concave function and affine, they cross at most 2 times. And that's the general idea. How many times do you cross? So if you cross at most, so if you cross twice, then you are majorized. That's the basic idea. So that's the statement. You are fixing, so you have a density with respect to some measure mu. So f and g are density function. You are fixing the first moment with respect to that measure. And now you are just looking at the shape of f and g. And you are just asking that they cross twice, which means that you have an interval for which g is less than f, and outside is the opposite direction. So if you see, yeah, I can't really, can I draw something here? Not really. Okay. So just draw a line basically and something above. That will be the next result. So that's yeah. So that's the general idea. If you cross twice, then you are going to be majorized. That's the conclusion. So under those constraints. So the proof is actually or kind of intuitive. The expectation constraint. So yeah, we have the. Let me see if I. Yeah, and I didn't mention the proof, but it's okay. It's very intuitive. We have actually a more general result where we can allow increasing function and not just phi. And we need that for moment bounds. But so that's yeah, that's the main result. So this theorem is kind of, let's say, folklore in some context. Not exactly maybe in this formulation, but that's how the bound for moments in the log-concave case is done. You basically use this statement. What we have is a bit more general, and we need that to, for example, get moment bound between all order, not just first moment and p moment, but alpha and beta. So again, if you have a log-concave measure and you allow an increasing function that match expectations, and you have convex order. And again, you are log-concave with respect to that reference measure Z. So Z is always log-affine with respect to, I mean, basically you take Z. If mu is a probability measure, Z is just same distribution as mu. So we need something that's affine. So the idea here is that if you are concave and affine, then you cross twice. Actually, you cross at most twice, but because you are density, you have to cross at least once. If you draw a picture, and if you cross only one, that will contradict the expectation condition. So the expectation condition tells you that you have to cross more than just. So that's the general idea. So again, you have like, if you draw a picture of a line and the concave functions, and they cross at most twice. And the constraint we have implies that they cross exactly twice. And now the application, then it's simple. You just take those specific convex function, and that gives you the application you want, concentration or moments or entropy. For tail-bound, you could actually have better things in some cases, actually, not using these techniques. These techniques you'll get only via the moment generating function. So this is a standard approach to get concentration bound, but it might not be optimal, especially for small deviation, but real small deviation, like close to the expectation. This technique is good when T is large. When T is close to expectation, then you need to have a different approach. And the approach I mentioned before, which was this kind of localization or extreme point problem, this will be better in this case. But if T is large and that's what you are looking for, then you can apply those well-known Chernoff type bound. And you need to understand the moment generating function or Laplace transform. And you can connect this to the Legend transform by if X is majorized by Z, by taking this. So it's a very standard approach. I will just write down the proof. You just look at Markov inequality and exponentiate. And you introduce a parameter lambda and you optimize over all lambda. So now, because you have a convex function, you get that the log Laplace transform will be less than the log Laplace transform of Z when if X is log concave with respect to Z. And basically, you just need to understand just one distribution to get that whole class. So you can get a much more general result if you understand just what log concavity you are with respect to what measure, then you can get the same result for the whole class, basically. So it's fairly interesting result. And so this is good again for large deviation when T is large. There are some questions where we're trying to understand how does the probability behave when X is close to the expectation, and those techniques won't work. And this is not convex. This is not a convex function, the probability itself. So to bound this probability, we go through Laplace transform, which is convex, but by doing that, you lose things, at least in the small deviation regime. So we have actually some follow-up results and where we can estimate those smaller deviations. So I think that's pretty much all I have for now. So thank you everyone for listening, and I will be happy to take any question.
Thank you very much, Arnaud, for the great talk. Are there any questions? I just have one question. I'm trying to understand. So if one random variable is log concave with respect to Z, is it true that their densities intersect at most twice?
Yeah, so but the other one has to be affine. If both are log concave, no, but one has to be affine.
One has to be affine.
Yes. Z is always affine with respect to Z to itself.
Okay.
That's the idea. Yeah, no, both log concave will not cross. You can have several intersections, but one has to be affine so that it's a straight line And by concavity, you go down, up, down, and that's it.
I see. And can you go one slide back? There was this first lemma. Yes.
Yeah.
Where do you use convexity of phi here in the proof?
So to prove this statement, we are reducing to those, you can reduce to x minus a plus, this kind of,
Linear function.
so it's in the proof, you can approximate any convex function by, let's say, like a function like this. You go like this, like this, like this.
Yes, yes.
And so basically, what
okay.
you prove
You
is that
reduce that inequality, and then you can rewrite it. Okay, I see.
Yeah, you reduce this to x minus lambda plus, or x minus t plus, and we, based on that equality here, you can estimate things, and then you get by approximation to convex function.
I see. Okay.
But now, maybe is it just a restriction of the method? Can we get more than just convex? This I don't know. Maybe there is something more, but this I don't know if you can get more than just convex. But in the approach, we just approximate by x minus t plus, and any convex function can be approximated by those.
Yes, yes.
But that's a good question. Can you have more general result than just convex? I don't have a counterexample where you get this. Yeah, this I don't know. Maybe there could be something more, but
Okay.
I'm not aware of that.
Any other questions in the audience?
Arnaud, hi, thank you for the great talk. I had a question about what you said regarding discrete log-concave sequences, that you don't have reverse holder inequalities in general.
So we have some, it's not going to be, so we have some bound like here. So if you just look at geometric, for example, the second moment, so in the continuous case, you have an expectation of x squared, which will be less than, I don't remember, 2 times expectation of x1, x, yeah. You don't have that in the discrete case. Just look at geometric. You are not going to have an upper bound on the second moment by the first moment up to some universal constant. Just with geometry.
But is there some nicer class, some like
reasonable
condition that you can impose?
So there are bounds where that's, so what we're able to get is that if you have a lower bound on the expectation, so if expectation of x is at least, let's say at least 1, then is going to be comparable. So you need to have some kind of constraint on it. Basically, we have a bound where we have an exponential 1 over expectation of x. So if that goes to 0, then the stuff blow up.
Okay.
It's not, but with geometric, it's not comparable. Now, if you look at just Poisson, or do you have a bound? I didn't check actually. The idea is just to check your class. So what happened with Poisson here, for example? We just look at just general log concavity. So in general, for log concave, you don't. Poisson, I don't remember if we check, but like what happened with the Poisson here. So maybe for some subclasses, you might have some result, but yeah, this will just need to check. I'm not sure about Poisson. We saw that for log concave, so we wanted something more general, but log concave is not exactly going to work. Try with Poisson. I don't remember what would be in this case. Yeah.
Okay, thank you.
Thanks for the question. Okay, the last question, not mathematical. This Carlin, is it this with name that starts with S?
Sorry.
This Carlin that you cite, is it the one who got Nobel Prize?
Carlin?
Yes.
Oh, I don't know.
Okay.
Nobel Prize in what area?
In economics, I think.
Maybe.
Carlin or Sharplin,
maybe.
one of them, I forgot. Okay.
It's possible. They were doing some famous research in that area. I don't know if one of them got.
Okay.
Yeah.
If
I will check on Wikipedia.
Yeah. If there are no any more questions, I guess let's thank the speaker again.